So problem 4.5, sum the following series. Okay, so we have a set of 8 series. All of them are convergent. Okay, so we don't need to check that. Although if it's a good exercise if you're not sure. Okay, you can use the techniques we have been using in previous exercises, right? For checking that these series are actually convergent. Okay. Now, so how to sum a series? Okay, how do we compute the value of a series? Well, in theory, we have seen 3 types of series that we know how to sum. Okay, the first one is the geometric series, right? So the geometric series is the sum from n equals 0 to infinity of x to the n. Okay, and this is equal to 1 over 1 minus x, where when x is the absolute value of x is smaller than 1, right? Otherwise it's not convergent. Now the second series we have seen is the arithmetic geometric series, which is the sum from n equals 1 to infinity of n times x to the n, which is equal to x over 1 minus x squared, and again when the absolute value of x is smaller than 1. Otherwise it's not convergent. And the final one are telescoping series, right? And these are series of the kind u sub n minus u sub n plus 1, right? So the general term can be written like that. And so these are the solution for this is u sub 1 minus the limit when n goes to infinity of u sub n, right? Check the theory videos if I'm not sure about this. Okay, so let's compute this series. Okay, so these are the only types that we will see, right? So if I ask you to sum a series, it will be one of these types, right? Okay, so the first one is the sum from n equals 0 to infinity of 3 to the n plus 1 minus 2 to the n minus 3 over 4 to the n, right? So we have, as you can see, there are two terms here, right? So we can separate this in 3 to the n plus 1 over 4 to the n, and then minus the sum from when n equals 0 to infinity of 2 to the n minus 3 of 4 to the n. Okay, now we can do this because this series is convergent, and these two series are convergent because we will see that they're types of geometric series, both of them. Okay, you can see that with some algebra we will get there, right? But the thing is, so when you have this series, the geometric series that are absolutely convergent, you can sum them and subtract them and do this kind of manipulations because they work as actual real numbers, right? Well, now here we have 3 to the n plus 1, which is 3 times 3 to the n. Okay, so the 3 can get out of the series. Okay, and this is over 4 to the n. And then here we can multiply by 2 cube, so we have 1 over 2 cube, and then we have 2 to the n over 4 to the n, right? Or we can rewrite it like this: 3 times 3/4 to the n from n equals 0 to infinity minus 1 over 8, the sum from n equals 0 to infinity of 1/2 to the n, right? Now this is the geometric series where x is 3/4, so the solution for this is 3 times, and then this is 1 over 1 minus 3/4, okay, and then minus 1/8, and the same thing with here is 1 over 1 minus 1/2, okay. Now this is 1 minus 3/4, this is 1/4, 1 over 1/4 is 4, okay. And then here this is 1 minus 1/2 is 1/2, 1 over 1/2 is 2. Okay, so what we have is 12 minus 1, let's see, 12 minus 2 over 8, or in other words 1/4. Okay, 12 is 48 over 4, so the result is 47 over 4. Okay, this is the value of this original sum. Okay, let's do part 2. Now part 2 is the sum from n equals 1 to infinity of n, and let me write it like this: 1 over 2 n to the n. Okay, so this is straight arithmetic geometric series, right? So this is n times x to the n, and x here is 1/2. So the solution to this is 1/2 over 1 minus 1/2 squared. Now 1/2 squared is 1/4, so then we have 4 that comes multiplying, so the solution for this is 2. Okay, easy enough. Now part 3 is the sum from n equals 0 to infinity of 4n plus 1 over 3 to the n. And as we did in part 1, we can separate this in two. So this is 4 times n that multiplies 1/3 to the n, and then the sum from n equals 0 to infinity of 1 over 3 to the n, right? As before, we can do this manipulation because both of these series are convergent separately. Okay, otherwise it's not guaranteed that the two things are equal to each other. Okay, so this is 4 times, and then this is an arithmetic geometric series with and this x is equal to 1/3, so this is 1/3 over 1 minus 1/3 squared. Okay, and then we have a geometric series with parameter 1/3, so we have 1/3 here. Now this is 1 minus 1/3, it's 2/3, and squared, this is 4/9. Okay, 4 and 4 cancel out, and then this is 9 comes multiplying, so this is 3, and then we have 1 over 1 minus 1/3, this is 2/3, and the division is 3/2. Okay, so we have 3 plus 3/2. 3 is 6/2, so this is 9 over 2. Okay. Okay, let's go to 4. 4 is the sum from n equals 1 to infinity of the square root of n plus 2 minus 2 the square root of n plus 1 plus the square root of n. Okay, well here there's nothing to the power of n, right? So this is not going to be either the geometric series or the arithmetic geometric series. So this is going to be a telescoping series. So we need to write this as u sub n minus u sub n plus 1, right? Where u sub n is the sequence. So now we have n plus 2 minus n plus 1, and then we have minus n plus 1 plus the square root of n, right? So we can write this like this, minus square root of n plus 1 minus the square root of n, okay, with a parenthesis here, right? And then yes, and then we have minus, wait a minute, this is correct, sorry, this is something, wait a minute, I'm stuck. So we need to write this in terms of u sub n and u sub n plus 1. Okay, so if u sub n will be something, the square root of, let's see, a times the square root of n plus 1 plus b times the square root of n, and u sub n plus 1 will be a times the square root of n plus 2 plus b times the square root of n plus 1, right? So then if we want to write this like this, this will be a times the square root of n plus 1 plus b the square root of n minus a the square root of n plus 2 minus b the square root of n plus 1, right? So here we have minus a is equal to 1 if we compare the coefficients here, right? And then we have b is equal to 1, right? So then, and then if we compare it, yes, we have minus 1 and minus 1. So if we substitute here, this is minus 1 and this will be 1. Okay, so that's the term we wanted. Okay, minus the square root of n plus 1 plus the square root of n. Okay, you can check that if you write like this, and then u sub n plus 1 is minus the square root of n plus 1, sorry, plus 2 plus the square root of n plus 1. Okay, and then if you subtract this, you can get this. Okay, and so in general, when you have telescoping series and you see this kind of structure, you can do this kind of testing that I did to find the coefficients. Okay, if you're not clever enough, which I am not. Okay, so this is the sum from n equals 1 to infinity of u sub n minus u sub n plus 1, where u sub n and u sub n plus 1 are these guys. Okay, and we know that this is a telescoping series. The solution for this will be u sub 1 minus the limit when n goes to infinity of u sub n. Now u sub 1 we substitute here. This is minus the square root of 2 plus 1. Okay, and then we have the limit. Let me write it here. Okay. I'm going to erase this. So u sub 1, this is equal to u sub 1, which is 1 minus the square root of 2. And then the limit when n goes to infinity of square root of n minus the square root of n plus 1. And in order to compute this, we have to multiply and divide by the square root of n plus the square root of n plus 1. By now you should be able to do this all the time, right? And then you have n minus n minus 1. So you have this cancel out, and then the limit of this is 1 over the square root of something of n that goes to 0. Okay, so the limit of this is 0. This value of the sum is 1 minus the square root of 2. Okay, now next let's do 5. Part 5. The sum from n equals 1 to infinity of the square root of n plus 1 minus the square root of n divided by the square root of n times n plus 1. Okay, this also stinks of telescoping series, right? So we can think of writing, this is the n squared plus n, right? Writing this as two separate fractions, right? So this can be, let's see, how to write this. We have n plus the square root of n plus 1 minus the square root of n divided by the square root of n times n plus 1. This is clearly something a plus b n plus 1, right? Okay, so a times the square root of n plus 1 plus b times the square root of n will be the square root of n plus 1 minus the square root of n. And so it's obvious that here that a is going to be 1, okay, and b is going to be minus 1. Okay, so let me substitute here. This is 1 minus 1. Okay, so we can rewrite this sum like this. 1 over the square root of n minus 1 over the square root of n plus 1. Okay, so this is a telescopic series where this u sub n, okay, u sub n is here. Okay, so the value of this is going to be u sub 1 minus the limit when n goes to infinity of u sub n. Okay, but u sub 1 is 1, and the limit of u sub n is going to be 0. So the solution, the value of the series is 1. Okay? to part 6. The sum from n equals 1 to infinity of the logarithm of n times n plus 2 divided by n plus 1 squared. Okay, so because of the properties of the logarithm, this is equal to, and we could say the logarithm of n divided by n plus 1 minus the logarithm of n plus 1 divided by n plus 2, right? If you don't believe me, you can check, right? So you just apply in the properties of the logarithm. You can pause the video and try to derive this. It's not hard, right? So now this is our u sub n. Okay, this is also a telescoping series. Okay, so then we have u sub 1 minus the limit when n goes to infinity of u sub n. So u sub 1 is the logarithm of 1 over 2, right? And the limit of this is the limit of the logarithm of n over n plus 1 is the logarithm of the limit of this, but this limit is 1, so the limit is the logarithm of 1, which is 0. Okay, so we are fine with this. The logarithm of 1/2, which is also minus the logarithm of 2. Okay? Okay, good. Now 7, and this is actually one of the fun ones. Okay? This is x to the integer part of n halves and y to the n plus 1 over half with the absolute value of x times y smaller than 1. Okay, so what's this function? Okay, this is the integer part of x, which means that, we've seen this before, this is the smallest integer so let's see, so it's the greatest integer that's smaller than the number. Okay, so for instance for n's we have n halves. Okay, if n is 1, then n halves, let's see, that n halves is 1/2, right? Well, the integer part of this is 0, 1/2. Okay, and so if we count from n from 1, 2, 3, 4, 5, 6, then the integer part of n over 2 is the integer part of 1/2, which is 0, then the integer part of 1, which is 1, then 3/2, the integer part of this is 1, then you have 2, 2, 3, 3, and so on. Okay, and then with n plus 1 over 2, you will have with n equals 1, this is 1 plus 1 over 2, 1. Then if n equals 2, this is 3/2, 1. Then 3 plus 1 is 4, over 2 is 2. 5/2 is 2.5. The integer part of 2.5 is 2, so it's 3, 3, 4. So you repeat, right, the numbers. Okay, so this is what the powers are going to be. So let me express that. Okay, expand this sum so that we can get some sense of this. Okay, we have y over n plus 1 over 2, right? And so we have the first term when n equals 0, both of them are 0, right? So then we have 1, and then so then, sorry, 0, 0, 0, 1. Okay, and then the second term when n equals 1, x is 0, the exponent of x is 0, and the exponent of y is 1, so then we have 1 plus y. And then you have plus x times y, right? And then you have plus x times y squared plus x squared times y squared plus x squared times y cubed, and so on and so forth, right? So it's easy to see, and if you don't believe me, you can pause the video and do it yourself. You have 1 plus y, and then with x you have x times 1 plus y, and then you have x squared y times let's see, no, sorry, that's x times y times 1 plus y, and then you have x squared times y squared times 1 plus y. And if you keep doing this, you will see that it's easy to prove as well, that this is actually 1 plus y summing from n equals 0 to infinity of x, y to the n. Okay? And now this is the geometric series with the parameter x, y, but we know that the absolute value of x times y is smaller than 1. So this is actually 1 plus y, which multiplies 1 over 1 minus x times y. Okay? And this is the value of the sum. Okay? And now the final exercise, the final part, we've done almost, is 8. The sum from n equals 0 to infinity of 1 over 2n, and then the cosine of 2 pi n over 3. Okay, so let's see what the cosine of 2 pi n over 3 looks like. Okay, so let's see, when this starts at 0, okay, when n equals 0, this is going to be 0. Sorry, 0, so the cosine of 0 is 1, right? Now when n equals 1, this is the cosine of 2 pi over 3, okay, so if you have this is the unit circle, right, and we can write the angle here. 2 pi over 3 is, let's see, this thing here, okay, so this is the cosine of this angle, right? So this is 120, actually, 120 degrees. The cosine of 120 degrees is 1/2. Okay, you can compute this. Now, if you go to n equals 2, this is 4 pi over 3. So then you get this thing, I think. Okay, and the cosine of this is also, okay, this is the symmetric, this is also 1/2. Now, when n equals 3, this is 3 times 2, 6 over 3, it's 2, sorry, it's 2, so it's the cosine of 2 pi, which is 1 again, okay? And then we repeat the same, because this is always, so we're going to 0, then this angle, and then this angle, okay? And we're repeating them in sequence, so the sequence of this is 1 minus 1/2 minus 1/2, and so on and so forth. Okay? So we can rewrite this sum like this. Okay? This is n equals 0 to infinity, and then we have 1. Sorry, yeah. So let me see how to write this. So then we have 1 values of 1 when n equals 0, 3. 6, and so on. Okay, so when n is a multiple of 3, okay, so we can write here 3n. Okay, we are going over the multiples of 3. Okay, and now we have minus 1/2, which is the value of this cosine, times from n equals 0 to infinity, or 1 over 2 to the 3n plus 1, which is because this is not this is n equals 1, this is n equals 4, so this is a multiple of n of 3 plus 1, okay, this is the following number, okay, and the same thing with the next one, okay, so we can divide the numbers in the series in 3, right, 3n plus 1 and 3n plus 2, we're dividing the natural numbers in them depending on if they're multiple of let's see, 3 or not, right? So then this sum here, the first one, is the sum from n equals 0 to infinity of 1 over, and then 2 cubed, and all of this to the n, right? And then we have here, there's an extra 1/2, so this is 1/4 sum from n equals 0 to infinity of 1 over 2 cubed to the n, and then we have an extra 1/4, so multiplying 1/2 is 1/8, and this is from n equals 0 to infinity of 1 over 2 cubed to the n, right? Okay, so let me erase this. And this series in the at the bottom are equal to this, right? So here is the geometric series with this parameter x being 1 over 8. So this is 1 divided by 1 minus 1 over 8. And then we have minus 1/4. And the same thing, 1 divided by 1, sorry, minus 1 over 8. And then minus 1/8 times 1 divided by 1 minus 1/8. Okay, so in other words, this is a common factor in all three terms. We have 1 minus 1/4 minus 1/8 that multiplies 1 over, and then this is 7/8, right? Now what's this part? This is, if we write everything as a multiple of 8, we have 8, okay, minus 2 minus 1. Okay, so this is 5, right? 5 divided by 8, and this is 8 over 7. So the solution for this series is 5 over 7. Okay? These last two ones are not as immediate as the other ones that we have seen, so please go over them if you are not clear on this. But yeah, that's the end of the exercise.